Hello, everybody. Welcome back. We are going to be doing the first lesson in Unit 2, and today's lesson, Unit 2.1, is all about types of chemical bonds. So let's get started. As usual, I always like to start my units with a little factoid, and I find this one to just be fascinating because Alaska is so large that actually it extends into the next hemisphere, which is just interesting. Anyway, so we are moving into Unit 2, which is all about molecular and ionic compounds, their structure, their properties. And the unit that we're going to be looking at today, Unit 2.1, is all about different types of chemical bonds. So what is a bond in the first place? It is not something physical. It is not something you can touch. A bond, a chemical bond, is a force that holds atoms together and makes them function as a unit. And an important question to answer is, why do atoms bond at all in the first place? I mean, what's the point? And the point is that atoms will try to achieve what's called the NGEC, the noble gas electron configuration, where you have that stable outer octet of electrons. And different elements will do different things to achieve that. For example, when you have a bond between a metal and a nonmetal, okay, that's an ionic bond. We see that metals tend to lose electrons or give away their electrons to form positively charged cations. They will lose their electrons to achieve that stable octet. Now, where do those electrons go? The nonmetals will gain those electrons to form negatively charged anions. So nonmetals gain electrons to achieve that stable octet. There is a transfer of electrons between metal and nonmetal. That's an ionic bond. If we're looking at two nonmetals, you know that is a covalent bond. There's not a transfer of electrons. This is two atoms sharing electrons in order to achieve that stable octet. So let's talk about ionic bonding first. This term in front of you, electrostatic attraction, that is a very fancy term that means something simple. Opposites attract. Okay, that is a force of attraction. That is what an ionic bond is. And again, it's formed between metals and nonmetals. Metals that easily lose electrons. Remember back to last unit, metals tend to have low ionization energies. That means electrons can relatively easily be taken away or lost. Metals will react with something that easily gains electrons. That's going to be your nonmetals. Again, remember from last unit, nonmetals tend to have high electron affinities. They take on or gain electrons readily. And those electrons are fully transferred from the metal to the nonmetal. Covalent bonding, however, we don't see that transfer. We see electrons being shared, okay? And you have different forces going on here. One of the forces is a force of attraction between the electrons of one atom and the nucleus of the other. And that should make sense to you. Electrons are negatively charged. The nucleus, because of the protons, it's primarily positively charged. Opposites attract. So there's a force of attraction right there between one atom and another atom. But there are also forces of repulsion. the electron cloud of one atom will repel the electron cloud of the other. Like charges repel, their nuclei also repel each other, again, like forces, like charges. And when you have this balance between the force of attraction and the force of repulsion, when those forces balance out, that is the length at which that bond has formed. And we'll talk a little bit more about that in a later unit. Polarity is a topic that comes up when we're talking about covalent bonding. Remember, guys, that back from Chem 1, a polar covalent bond means those electrons that are being shared are not being shared evenly, equally, which means that one end of that covalent bond, the one end where the electrons are hanging out, that's going to be a slightly more negative charge. The other end will be slightly positive. We use this Greek symbol for delta, and I'll to indicate polarity, and I'll show that to you in just a minute. But something that I really want you all to understand is that there's a spectrum, there's a gradual spectrum here. There isn't a hard and fast place where something is no longer ionic, now it's polar covalent. It's a range. You know, an ionic bond involves electrons being fully transferred from one atom to another. Polar covalent, the electrons aren't transferred, but they are kind of leaning to one side. And of course, nonpolar would be electrons are shared evenly, equally. But it's a gradual progression. There aren't these hard and fast boundaries between these words. Right here is some of that notation I was telling you about. We're using HF as an example here, okay? And this image here is showing me that fluorine is attracting the shared electrons more than hydrogen. Now, how did I know that? Because of this little symbol right here, that delta and then the negative. That's telling me that the fluorine end of this bond is the more negative end of the bond. The hydrogen end is the more positive end. So those shared electrons must be sort of leaning more towards the fluorine side. Also, this arrow, if you ever see that, an arrow with a little plus sign at the end, the arrow will always be pointing to the element that is attracting the electrons more than the other. So we say that this is a polar covalent bond. Sometimes you'll see this term right here. We say that the bond is experiencing a dipole moment. That's just a fancy way to say it's polar. Okay, we're saying the same thing, just differently. Polarity all comes down to electronegativity. And I want to review that term with you back from our last unit. Electronegativity is the ability of an atom in a molecule to attract those shared electrons towards itself. And there's a chart in our textbook that has the values for each element. They're called Pauling values. You do not need to memorize them. Okay, what I do want you to remember, however, is the trend in electronegativity on the periodic table. If you all will recall, which corner has the most electronegative elements, that is the upper right corner. Now, we ignore the noble gases because they don't tend to form bonds with anything. Some do, but most don't. So ignoring the noble gases, fluorine is your most electronegative element. It attracts electrons more than any other element on the periodic table. At the other extreme, in the lower left, francium is the least electronegative. However, guys, these actual values are less important. What is more important is the difference in those values between the two atoms involved in the bond. So the difference in electronegativity is the key here, okay? If the difference between two elements is 0, that means these two elements are sharing those electrons equally. So that's a nonpolar covalent bond. If the difference between them is intermediate, we would call that a polar covalent. If the difference between them is a large value, we would say it's ionic. But let me say again, because I know I've been teaching this class a long time, I know what you're thinking. What's an intermediate value? What's a large value? Can you give us some numbers? No, I can't. It's a spectrum, guys. It's a range. There isn't a number where we say, okay, this is intermediate, this is polar covalent. Well, nope, that number's too large. Now it's ionic. There isn't a cutoff, okay? It's a gradual spectrum, okay, where things develop covalent character or ionic character. However, let me alleviate some of your worry. Some of you might be thinking, well, how am I going to know? Guys, keep it simple. Go back to Chem 1. If you see a bond between a metal and a nonmetal, it's ionic, period. If you see a bond between two nonmetals, it's covalent, okay? And in general, if it's between two different nonmetals, it's going to be polar. If it's the same two elements, like chlorine and chlorine are bonded together, that's going to be nonpolar. Okay, so don't worry about where are the boundaries here. Just know that it is a spectrum. So I've got a couple of practice problems here for you. So what I've just put a periodic table image here just to kind of give you a reference. It says, without looking up the electronegativity values, order the following bonds according to increasing polarity, meaning which one is the least polar, which one is the most polar. It's not about the electronegativity values, it's about the difference. So pause the video, see if you can figure this one out. All right, so in general, guys, we were looking at those 4 elements right in that area there, okay? It's all about the difference in electronegativity. Fluorine is the most electronegative element on the periodic table because it's in that corner, okay? Of those 4 elements that we're looking at, carbon is the least electronegative. So we are going to see the greatest difference in electronegativity between carbon and fluorine. This is the most polar bond. Fluorine bonded to fluorine has an electronegativity difference of 0. This is the least polar. It's not polar at all. It's nonpolar. So if I'm going to give that a value of a 1, that's the least polar. And CF is the most polar. I'm going to give that a value of 4. What's going to come into that number 2 position? That's going to be this guy. And then he's going to be the third runner, third place finisher. Okay? You don't even need these values. You can look at simple distance. How far apart are the elements on the periodic table? The more far apart they are, the greater the electronegativity difference. All right, let's look at another one. This question says, a student claims that F2 is more polar than H2 because fluorine has a higher electronegativity value than hydrogen, and I've given you those values. Do you agree with this claim? Explain why or why not. So pause your video and think about it. All right, in a question like this, where you're asked, do you agree with this claim? You first need to actually answer the question. Yes, I agree, or no, I disagree. And I hope your answer was that you disagree with this statement. Then you have to explain why. All right, so if we think about these two diatomic molecules here, again, it's not about the values themselves, it's about the difference. Yes, fluorine is more electronegative than hydrogen, certainly it is. However, the difference in these two molecules, both of them have a difference of 0. They are equally polar. In fact, they're not polar at all. They're both non-polar bonds. So make sure you actually answer the question and then you back it up. All right? So we've talked about ionic bonds, covalent bonds. I just have one more slide about metallic bonding, okay, which is obviously between atoms of metals. And this image that you see in front of you is kind of what a metal looks like if you were to zoom in on it with a microscope. And we see something called delocalized electrons. That's what these little purple dots are, these little ones. Delocalized just means can move around easily. So a metal is nothing more than positively charged cations with electrons flowing through them like water almost, okay? And sometimes you will see metallic bonding described as a sea of electrons, meaning electrons can flow so well and so easily, it's almost like they're flowing like water, which is why they are such good conductors of both heat and electricity, okay? Because charge can flow like water. So any metal on your periodic table is going to have a structure like what you're seeing in that picture there. So guys, that is it for Unit 2.1. And I hope you've learned a little something today, and I look forward to seeing you next time.